tree method is good for interpretability. So using tree method, because decision tree is pretty much same as a human decision process. So using tree, you can very easily explain why you have made such decision. So you can very easily explain or convince your boss or other guys using decision tree, because decision tree has some step-by-step structure, and this clearly includes some reasoning. So you can very easily explain why we have to choose this decision, why we have to choose this decision, which input predictors is important for making your decision, and so on. But tree method has very important drawbacks. So, first of all, tree method is unstable, which means if you change few data point, then the outcome can totally different. Okay, your decision tree before and after you tweaking few data point can be totally different. And also your tree has lack of smoothness. So let's go back to the process you build decision tree. At the beginning, you have just entire input space, and at each time you introduce one simple binary decision. So you have these different areas, and for each area you assign one single value or class label so that your decision tree can make decision for every entire space. And when you look at these partitions, this is very artificial, very non-smooth. Okay, so naturally the result function, the function coming from these partitions, is just a step function, non-smooth, very unnatural. So we can expect very high generalization error. Okay, so usually if you use just one single decision tree, the accuracy usually worse than the other machine learning approaches because of this totally non-smooth property. So yeah, this is good for explanation, but if you want to find out very accurate algorithm, tree-based method is not a good idea. Okay, and for this purpose, people invent bagging and boosting. These two kind of ensemble approach is very important and very nice. So many challenges in Kaggle. The winning algorithm, most of winning algorithm exploit bagging or boosting ensemble method. Very powerful and simple. I'll explain. So in the cross-validation section, we have already discussed what is bootstrapping. Sorry. What was bootstrapping? Bootstrapping basically has original data point. There are n data point. This is original. n data point. And from the original data point, you can generate many replicas using random sampling with replacement. You can build one data set, new data set, using random sampling. So at each time, just pick one of your data point uniformly random, and you repeat this process n time independently. Then you can have n different data point, which comes from original data set using uniform sampling. So you can generate data set as many as you want. And this is bootstrapping. Bagging is, the name of bagging comes from bootstrap aggregation. And the idea is, so bagging. So the idea is you generate many different data sets using Bootstrap and then train trees using each data set. So generate one decision tree, another decision tree using this data set, another decision tree, another decision tree, another decision tree using each Bootstrap dataset. And then combine the decisions. Very natural aggregation technique is take average, which means so you generate m different trees using m different Bootstrap dataset. And for inference or for tests, you can simply use m different dataset independently and make a prediction in m different ways because we have m different trees, and then aggregate them using just average. Because we train many different trees, maybe the outcome will be very accurate. Very cute idea, isn't it? And the Bootstrap method has out-of-bag data. For each bootstrapping, we do not use entire our training data point because at each time we just randomly sample one of data point uniform random with replacement. So some of data will be selected from the process and some of them will be selected multiple times to build one new data set, but some of them never selected for building one particular new data set and remain there. And this blue point is called out of bag. And because this blue point is not used for training, is not utilized for training, we can use this blue data point for your test purpose. Okay, so you first train your one decision tree using this data point and then verify your quality of decision tree using out of bag. So this is one side remark of bagging method. Okay. So bagging is very cute idea and we can improve the accuracy using bagging. Bagging is very nice. But the problem is, so many researchers actually employ the bagging method and they implement the bagging method for many different applications. But they observe that although you increase the number of data set or number of decision trees by the bagging method, although they increase the number of the tree to infinity, the improve the performance becomes very minor. And when they look at each decision tree obtained from each bootstrap data set, it turns out that each tree looks like very similar with other tree. And the main reason is this. Although we build another data set using random sampling, but most of data overlap with other randomly generated bootstrap dataset because every data point comes from one common original dataset. Okay, so because of this similarity, the simple bagging method has limitation. Although you increase the number of tree to infinity, your quality of performance was so not such great. So people invent random forest. Random forest, the main concept of random forest is let's make decorrelated trees. How to make decorrelated trees? The concept is very simple. At the beginning, we have this entire input space, and at each time, we learn kind of greedy approach to generate a decision tree. And usually, in original decision tree process, we consider all input predictor to find out one binary simple condition. We check every single predictors and which we find out which predictor give us the most significant improvement. Okay, and usually this step make all the decision tree looks like same. So in the random forest, we do not use entire input predictor. We do not use entire input variables, but we randomly sample m predictors from P predictors. Here M is less than P. So in this case, we have two input predictors, and so at each time, we just flip a coin. If head comes on, we choose X1, and just find the condition, only use the X1 input predictor. If tail comes up, then we choose the X2 and just find condition among the all possible binary condition using X2. Next step again, randomly sample predictors and then make one condition and so on. Because of this random process, random selection, we can decorrelate our trees. Because of this random selection, all decision trees has some different properties, so the ensemble becomes more meaningful. Different decision trees has its own some kind of meaning, so the combination of output has more powerful or rich decisions. So we can expect better test error compared to the simple bagging method.